Imagine humanity far in the future, not just living on one planet but spread across space, always hungry for energy, because energy is life for any civilization. It runs homes, cities, ships, computers, and dreams, and sooner or later every smart species hits the same wall. Stars don't last forever, planets are limited, and the universe doesn't hand out infinite fuel for free. So naturally curious minds start looking at the most powerful objects out there, and nothing beats a black hole. Not in mystery, not in strength, not in raw energy potential. Because a black hole is not just a cosmic vacuum cleaner, it's a machine made by nature itself. The most efficient engine the universe has ever built. And the big question becomes not, what is a black hole? But can we use it? The first idea comes from something called rotation. Because most black holes spin insanely fast, some close to the speed of light. And when something spins that fast, it doesn't just spin itself, it drags space and time with it like thick honey. And around a spinning black hole, there's a strange zone where nothing can stay still. Even light is forced to move in circles. And in this zone, energy can be stolen in a clever way. Not by touching the black hole, not by crossing the point of no return, but by playing with motion and gravity like a cosmic trick. The idea is simple at heart, even if the physics is wild. You send an object toward the black hole. It splits into two pieces. One piece falls in such a way that it actually takes away some of the black hole's spin, while the other piece escapes with more energy than you started with, meaning the extra energy came straight from the black hole itself. And this is not science fiction. It's allowed by the laws of physics, tested with math, simulated on computers, and even observed in indirect ways around real black holes in space. And the beauty of this method is that it doesn't destroy the black hole, it slowly slows it down. Like using a windmill to drain energy from the wind. And the pros here are huge. You get clean energy, no waste, no smoke, no radiation poisoning, and an energy source that could last millions or billions of years. But the cons hit hard too. Because to do this, you need perfect control, perfect timing, materials that can survive insane gravity, and technology that can operate where space and time behave like a funhouse mirror. And one tiny mistake means your equipment is gone forever, crushed, and stretched into nothing. And even if you master it, the amount of energy you get per operation is limited. So you need massive systems, thousands or millions of launches, and a civilization that can afford to lose hardware without crying over it. Then comes another idea that sounds even crazier but is deeply fascinating, and that is the fact that black holes are not eternal prisons. They slowly leak energy, not because anything escapes from inside, but because empty space itself is not really empty. It's buzzing with tiny particles popping in and out of existence. And near the edge of a black hole, one of these particles can fall in while the other escapes, stealing a tiny bit of energy from the black hole, and over insanely long times. The black hole shrinks and fades away, releasing energy the whole time. And this is called Hawking radiation. And for big black holes like the ones formed from stars or sitting at galaxy centers, this radiation is laughably weak, colder than deep space itself, useless for power. But here's where imagination kicks in. Very tiny black holes, if they exist or could be made, would release enormous energy, more than nuclear bombs, continuously. And the pros of this idea are mind-blowing because such a black hole would be the ultimate battery, tiny in size, massive in power, producing steady energy for years, decades, maybe longer, and you could, in theory, feed it matter to keep it stable and control its output like adjusting a flame. But the cons are terrifying because we have never seen such small black holes. Creating one would require energy beyond anything humanity can currently imagine. Containing it would be harder than containing a star, and if control fails, you're not dealing with a fire or a reactor meltdown. You're dealing with a gravity monster that could destroy everything nearby in moments. So while this idea excites physicists, it also scares them because it's one of those technologies where success means godlike power and failure means total disaster. Now let's move to the most realistic and already proven way black holes release energy. And this one doesn't rely on fancy tricks or quantum magic. It relies on the simple fact that falling is powerful. When matter falls into a black hole, it doesn't drop straight in. It spirals, crashes, heats up, glows, and screams with energy before crossing the final edge, and this swirling mess is called an accretion disk. And it is so energetic that it can outshine entire galaxies, converting matter into energy far more efficiently than nuclear fusion, which powers our sun. And this is where black holes truly shine as engines. Because while fusion turns a small fraction of mass into energy, a black hole's gravity can turn nearly half of that mass into usable energy before it disappears. And the pros here are strong and practical compared to other ideas. We already see this happening in space. We know it works. We know the energy output is insane, and in theory, a future civilization could build collectors far away, safely outside the danger zone, and capture the radiation, heat, and particles streaming out from the disk, turning them into electricity or propulsion power, and this could run cities, planets, or starships. But again, the cons remind us why this is future stuff, because you need to control the flow of matter into the black hole. Too much and you destroy your setup, too little and the power drops. And the environment around an active black hole is violent, full of radiation, shock waves, magnetic storms, and jets that shoot energy across space like cosmic lasers. So your machines would need to survive conditions far worse than anything near a star, and repairs would be extremely difficult, slow, and dangerous. There's also a deeper, more philosophical downside that students should think about, and that is dependence, because once a civilization builds its entire energy system around a black hole, it becomes tied to it politically, technologically, and even culturally, and losing access to it through disaster or conflict could mean collapse, just like how modern society depends on electricity today, but multiplied 1,000 times. Then there's another angle people don't often talk about, and that is using black holes as engines for movement, not just power plants, because if you can control how energy and matter fall in, you can create thrust, pushing ships using gravity itself. And this could allow travel between stars at speeds we currently dream about. And the pro here is clear: faster travel, deeper exploration, and access to the universe on a scale never seen before. But the con is again control, precision, and safety, because miscalculations near a black hole don't give second chances. Another important thing students should understand is that black holes are not evil objects. They don't hunt planets. They don't suck everything in. They obey physics like everything else. And that's actually a pro, because predictable behavior means usable behavior. But the con is that physics at that level is extreme, meaning even tiny errors in understanding can lead to massive failures. There's also the ethical side, because creating or moving black holes, if that ever becomes possible, raises questions about responsibility, risk, and who gets to decide where such power is used, because black hole energy could light up civilizations or wipe them out, depending on intention and wisdom. When you put all of this together, the picture becomes clear and exciting at the same time. Black holes are not just the end of things, they are also beginnings, powerhouses, teachers of deep physics, and mirrors showing how small we still are. And the biggest pro of studying black hole energy today is not that we'll build one tomorrow, but that it pushes students to think bigger, to mix imagination with science, to understand gravity, energy, space, and time more deeply, while the biggest con is thinking it's magic or easy, because it's not. It demands patience, humility, and generations of learning. In the end, harnessing black hole energy is like standing at the edge of the ocean before humanity learned to sail, terrifying, beautiful, full of promise, and full of danger. And whether we ever succeed or not, the journey toward understanding it will still power minds, inspire careers, and expand knowledge, which might be the most important energy of all. Now let's zoom out a little and think like future engineers and students who are not just dreaming, but actually planning. Because once the idea of using black hole energy exists, the next natural question is not, is it possible? But how would we live with it? And that's where things get even more interesting. Imagine a civilization that has finally reached the level where building near a black hole is no longer madness but routine, where ships move in and out of high-gravity zones like airplanes move through storms today. And in such a world, black hole power stations would not look like giant glowing monsters. They would likely be quiet, distant structures floating far away, carefully placed so that danger stays controlled. And the biggest advantage of this setup would be stability, because unlike Stars that flare, age, and explode. A black hole is incredibly steady. It doesn't burn fuel the way a star does. It simply sits there, waiting, meaning energy production could be planned centuries ahead, which is a dream for any advanced society. But the downside is psychological as much as technical, because living off something that represents destruction in popular imagination would require education, trust, and a deep understanding of science. Otherwise, fear would rule decisions, and fear plus powerful technology is never a good mix. Another major benefit that often gets overlooked is efficiency of space, because a black hole, especially a small one, packs insane energy potential into a tiny region, meaning future cities or space habitats wouldn't need massive star-surrounding structures like Dyson spheres. They could instead rely on compact, centralized sources, freeing up space for living, research, and travel. But again, centralization is also a weakness, because any system that relies too heavily on one source becomes fragile if that source is threatened by natural events, accidents, or even conflict. Speaking of conflict, students should really think about this part carefully, because history shows that every powerful energy source eventually becomes part of politics and warfare, and black hole energy would be no exception. In fact, it would raise the stakes higher than ever before, because controlling such energy could mean controlling entire star systems. And while one civilization might use it to power hospitals, schools, and exploration, another might see it as the ultimate tool for dominance. And this is a serious con, because the more powerful the energy source, the more damage misuse can cause. And unlike traditional weapons, mistakes involving black holes could have long-lasting effects on space itself, not just on people. There's also the problem of learning curve, because black hole physics is not something you master quickly. It demands deep knowledge of math, physics, engineering, and computing, meaning societies that fail to invest in education would be locked out of this future entirely, while those that do invest would leap far ahead, creating an uneven universe where some civilizations soar and others stagnate. And that gap could create tension, fear, and misunderstanding. On the brighter side, the pursuit of black hole energy would massively boost scientific progress, even if the final goal is never fully reached, because to even attempt it, humans would need breakthroughs in materials that don't break under extreme forces, computers that can predict chaos accurately, and medical science that can protect living beings from intense radiation. And all of these advances would improve life everywhere, not just near black holes. Another fascinating angle is environmental impact, because compared to many energy sources, black hole energy is surprisingly clean at the point of use. No smoke, no chemical waste, no carbon pollution, and for a species worried about damaging planets and ecosystems, this could be a huge pro. But the con lies in the source side, because feeding matter into a black hole means redirecting asteroids, planets, or stars, and that could reshape solar systems permanently, raising ethical questions about whether efficiency justifies cosmic destruction. Students should also think about scale, because black hole energy is not an all-or-nothing deal. A civilization could start small, capturing tiny amounts of radiation from far away, learning slowly, making mistakes safely, and building confidence over centuries. And this gradual approach is a big pro, because it reduces risk, but it also means progress would be slow, testing patience in a universe where faster progress often wins. There's also a human element that's easy to forget: curiosity, because even if black hole energy turned out to be too dangerous or impractical, the attempt itself would still answer deep questions about reality, about time, space, and existence. And that knowledge alone is priceless, inspiring generations of students to study science, not just for profit or power, but for understanding. And the con here is only if society loses sight of curiosity and focuses only on control and exploitation. As we continue imagining this future, it becomes clear that black holes are not just energy sources. They're crossroads where science, philosophy, ethics, and imagination meet. And that's why studying them is so powerful for students today, because even if none of us ever touch one, the thinking skills developed by wrestling with these ideas prepare minds to solve problems we haven't even discovered yet. And the story doesn't end here because there are still stranger possibilities, like combining black hole energy with artificial intelligence, or using black holes as long-term storage for information, or even as anchors for future space civilizations. And each of those ideas brings its own set of rewards and risks, which we'll dive into next as we keep moving deeper into this cosmic adventure. Now, let's imagine how students of today might actually become the builders of tomorrow, because every giant leap in science starts as a classroom question, and black hole energy is one of those questions that forces the brain to stretch. One of the biggest advantages of thinking about black holes as energy sources is that it completely changes how we see danger, because instead of running away from extreme environments, future humans would learn to work with them, just like early humans learned to use fire instead of fearing it. And this mindset shift is powerful. It teaches that nature's most violent forces are not always enemies. Sometimes they are teachers, showing us how energy really flows in the universe. But this mindset also has a dark side because confidence can turn into overconfidence. And history shows that civilizations often fail not because they lack knowledge, but because they think they have enough when they don't. And near a black hole, overconfidence is deadly. There are no warning signs, no second chances, just physics doing what it always does. Another exciting possibility is how black hole energy could reshape daily life in the far future. Because if energy becomes almost unlimited, many problems we fight today simply fade away. Water can be cleaned easily, food can be grown anywhere, planets can be warmed or cooled, and long space journeys become normal. And this is a huge pro, because energy scarcity is at the root of many conflicts. But the con is that unlimited energy does not automatically create wisdom, kindness, or fairness. And without strong values, powerful tools often deepen inequality instead of fixing it. There's also a beautiful connection between black hole energy and education itself, because to manage such systems, future societies would need generations of thinkers trained not just to memorize facts, but to question assumptions, test ideas, and accept uncertainty. And that kind of education benefits everything from medicine to art. But the downside is that it requires long-term planning, something humans have historically struggled with, especially when short-term gains are tempting. Now let's touch on something that really fires the imagination, the idea of safety zones and distance, because contrary to movies, you wouldn't build a power station right next to a black hole. You keep it far away using light, particles, and magnetic fields to move energy where you need it. And this distance is a massive pro because it lowers risk and makes the whole idea more practical, but it also means energy losses, complex systems, and constant monitoring and complexity always increases the chance of failure. Another overlooked pro is inspiration, because black holes already capture human curiosity like few other things, and turning them from symbols of death into symbols of progress would deeply affect culture, art, and storytelling, motivating students to study science not because they have to, but because they want to understand the universe they live in. And the con here is subtle, because romanticizing such powerful objects can also lead to misunderstanding, myths, and fear if education doesn't keep up with imagination. As technology grows, black hole energy would likely not replace all other energy sources, but join them, creating a balanced system where smaller needs are met by safer methods and larger projects rely on extreme sources. And this balance is a strong pro, because diversity increases resilience. But the con is coordination, because managing many energy systems at once requires cooperation on a scale humanity has rarely achieved. There's also the question of time, because black holes operate on timescales that make human history look tiny, and planning around them would force societies to think not just in years or decades, but in centuries and millennia. And that long view is a gift, teaching patience and responsibility. But it's also a challenge, because political systems and human emotions are often short-lived. Students should also think about failure modes, because every system fails eventually, and with black hole energy, failure planning would be as important as success planning, meaning building escape routes, shutdown methods, and layers of protection. And while this increases safety, it also increases cost and complexity, slowing progress. As we keep going, it becomes clear that the real power of black hole energy is not just the electricity it could provide, but the way it forces humanity to grow up intellectually, to stop thinking like planet-bound creatures and start thinking like a spacefaring species. And that transformation is both exciting and frightening. And still, we haven't reached the strangest ideas yet, because beyond power and travel, black holes may play a role in how information is stored, how time is measured, and how civilizations leave messages that last longer than stars, ideas that push the mind even further. And that's exactly where the journey takes us. Next, one of the strangest and most exciting ideas is how black holes could change the way we store and protect knowledge. Because information is a kind of energy too, and future civilizations might use the extreme stability of black holes as reference points, memory anchors, or cosmic libraries, not by throwing books into them, but by placing data systems around them that can survive longer than planets or stars. And the pro here is incredible longevity, messages, records, and discoveries preserved for millions of years, allowing future students to learn directly from ancient minds. But the con is that placing anything valuable near a black hole requires perfect planning, because one wrong move and centuries of knowledge vanish forever. There is also the idea of time itself, because black holes bend time in extreme ways, and learning to work near them could give scientists new ways to measure time accurately across vast distances, helping coordinate space travel and communication. And this is a huge advantage for a civilization spread across stars, but also challenges our basic understanding of reality. Because when time flows differently in different places, ideas like fairness, age, and even life stages become complicated, raising social and ethical questions that science alone cannot answer. Another powerful benefit of black hole research is how it unites different fields of study. Because to even talk about black hole energy, you need physics, engineering, math, computer science, philosophy, and even psychology working together. And this teamwork is a major pro, because it breaks down walls between subjects and teaches students that real problems are not solved in isolation. But the con is that collaboration on this scale is difficult, slow, and sometimes messy, especially when cultures, languages, and priorities clash. There's also the role of artificial intelligence, because no human mind alone could manage the constant calculations needed near a black hole. So advanced AI systems would become partners in exploration and control, predicting dangers, adjusting systems, and learning from mistakes. And the pro is increased safety and efficiency. But the con is trust, because relying too heavily on machines raises questions about control, responsibility, and what happens if the system makes a choice humans don't understand and time stop it. Another angle students find fascinating is the idea of using black hole energy to reshape entire regions of space, moving asteroids, building habitats, or even guiding the formation of new stars. And the pro is creative power on a cosmic scale, turning space from a passive environment into something we actively design. But the con is that such power blurs the line between exploration and interference, forcing humanity to decide whether it has the right to reshape the universe simply because it can. As we think about all this, it becomes clear that black hole energy would never be just a technical project. It would be a cultural turning point, changing how stories are told, how heroes are defined, and how success is measured, because bravery would no longer mean physical strength alone, but patience, discipline, and respect for forces far greater than ourselves. There is also a quiet but important pro that often gets ignored: humility, because studying black holes constantly reminds us how small we are, how little we still know, and how careful we must be. And this humility can protect civilizations from reckless decisions. But the con is that fear can also grow from the same realization, slowing progress if curiosity is replaced by panic. Another thing students should reflect on is failure as learning, because early attempts to harness black hole energy would almost certainly fail in small ways. Equipment lost, plans adjusted, theories corrected. And while this trial and error process is a pro for scientific growth, it also demands a society that accepts mistakes as part of progress, something not all cultures handle well. As this future unfolds in our imagination, black holes start to look less like monsters and more like mirrors, reflecting our values, our discipline, and our ability to balance ambition with care, and that may be their greatest lesson of all. And still, the journey is not over because there is one final layer to explore, the question of legacy, what it would mean for humanity to leave behind systems, knowledge, and energy sources that outlive planets and stars, and how black hole energy fits into that long, quiet conversation with the future, which is where the story takes its last, deepest turn next. We move into the final stretch of this long thought, where everything comes together and starts to feel less like science alone and more like a message to the future. When we talk about black hole energy in terms of legacy, we are really asking what kind of species humanity wants to be, because building something around a black hole means thinking far beyond a single lifetime, a single generation, or even a single civilization. It means planning for futures where the people who benefit from your work may not even remember your name. And that is both beautiful and challenging. One clear advantage here is continuity, because black holes last longer than stars, meaning any system built around them could provide stability through cosmic changes, star deaths, and planetary shifts, giving future societies a reliable anchor in an ever-changing universe. But the downside is commitment, because once such a system exists, future generations inherit not just its benefits, but also its risks and responsibilities, and they may not have chosen that path themselves. There is also a deep educational value in this idea of legacy, because students who learn about black hole energy are forced to think long-term, to imagine consequences far ahead, and this kind of thinking improves decision-making in every area of life, from environmental care to social planning. Yet the con is that long-term thinking often conflicts with short-term desires, and balancing the two has always been one of humanity's hardest struggles. Another powerful pro is unity, because projects involving black hole energy would likely be too big for any single nation or group, requiring cooperation across cultures and worlds, and this shared goal could reduce conflict and build a sense of collective identity. But history also warns us that shared power can lead to shared tension, disagreements over control, and debates about fairness that test even the strongest alliances. There is also the emotional side of legacy, because knowing that your work contributes to something that may last longer than Earth itself can inspire meaning and purpose, especially for young minds searching for direction. But the con is pressure, because not everyone wants the weight of eternity attached to their choices, and such pressure can slow creativity if not handled with care. As the story of black hole energy comes full circle, it becomes clear that whether or not humanity ever truly harnesses it, the idea itself already serves a purpose. It pushes students to ask better questions, to connect different fields of knowledge, and to respect the power of nature without fearing it blindly. Black holes, once seen only as endings, become symbols of responsibility, patience, and deep curiosity, reminding us that progress is not just about reaching farther, but about understanding more deeply. In the end, the greatest pro of exploring black hole energy is not unlimited power, faster travel, or cosmic engineering. It is the growth of the human mind, the ability to imagine futures that demand wisdom as much as intelligence. And the greatest con is forgetting that power without understanding is always dangerous. So this long journey doesn't really end with a machine or a power plant. It ends with a question handed to every student who hears this story. If one day we stand near the strongest objects in the universe and learn to use their energy, will we be mature enough to deserve it? And that question, more than any equation or invention, is what truly shapes the future.